All right, this is going to be the first of hopefully many videos on classical mechanics physics. For these videos, I will be referencing the Classical Mechanics book by John R. Taylor. It is a book I cannot recommend enough if you're going to be learning about classical mechanics. This video is going to be a bit of an introduction on some useful operations, some coordinate systems, and Newton's laws. It'll be pretty quick, and in the next couple of videos, I will go over some examples from this book that I think will be good practice for what we learn. All right, but getting started, the first thing I want to talk about is vector operations. All right, these are going to be the dot product and the cross product. These are not super difficult, but they are super useful. Starting with the dot product. Algebraically, what this is going to look like is if we have two vectors given the r vector, say, let's go 1, 2, 3, no. R1, R2, R3, and the S vector, S1, S2, S3, R dot S, denoted by a dot. There's a couple ways you can represent this algebraically, but that is going to be, you can do the length of the vector, the magnitude of the vector, multiplied by the magnitude of the other vector, times cosine of the angle between them. Or what you can do is just multiply them component-wise. So you would have, here we go, we'll go R1, and you multiply that by S1, R1, S1. And then you would do plus R2 times S2. And then, and then you would do plus R3 times S3. And this is going to give out some number, which is going to be a scalar, so just a number, no direction. Scalar. And what this is going to look like geometrically, maybe I'll change this. Maybe I'll give an example. If this, back to what I was doing before, 1, 2, 3, 3, 4, 5. This would be 1 times 3, so 3, plus 2 times 4, 8. Here we go. Plus 3 times 5, 15. So this is going to be equal to 26, I believe. And just the number 26, just a scalar number 26. Okay, and what this is going to look like geometrically is if we have this vector R, and we dot that with, here we go, vector S. What we are doing is we are taking the projection of S onto R. So this is going to come this way, and this is going to be a 90-degree angle. The important part is this is 90, this projection. And what this is saying is how much of S is inside R. This guy here is what this is showing us, how much of S is inside of R. The next important part of vector operations is going to be the cross product. Slightly more difficult than the dot product, but this is going to be denoted as is R cross S, again with our two vectors R and S from before. And the almost the only way I've ever done cross products is by doing the determinant of the matrix created by these two vectors. And so this would be, you'd have some amount in the x hat direction, some amount in the y hat, and some amount in the z hat direction. And the first vector goes in the middle. So this would be, if we take R from above, this would be 1, 2, 3, and then S would go on the bottom, 3, 4, 5. This could also look like where the determinant is denoted as just a vertical line. Y hat, Z hat, 1, 2, 3, 3, 4. And the way we do this, take the determinant of this, if you have not seen this before, is you will cross out the direction you want to go. So this is in the x hat direction. And you will do 2, in this example, it'll be 2 times 5 minus 3 times 4. And this is in the x hat direction. Oops. And then you'd cross out, this is going to get a little messy. Maybe do some of this. But then you would cross out the y hat direction and the z hat direction. And you would do minus the y hat direction because you want to alternate the signs of the directions. And then you would do the same thing as before, but with now the middle column crossed out. So it'd be 1 times 5, so 5, minus 3 times 3, 9. And that is in the y hat direction. And then again, plus, and then cross out the z, the vertical and horizontal of z. And then we do 1 times 4, that's 4, minus 2 times 3, 6. And that is in the z hat direction. And this is going to give us a vector where the dot product gave us a scalar. The cross product is going to give us a vector. This is going to be what, 10 minus 12 negative 2x hat 5 minus 5 minus 9 is negative 4 minus negative 4 is going to be plus 4y hat, and plus 4 minus 6 negative 2 z hat. So this vector here is going to be our curl. Not curl, that is something else we will learn about, but it is defined by the cross product. And what this is geometrically is a little bit more confusing, a little bit more in depth. But if we have some coordinate system x, y, z, let's see, so x, y, z, if we have two vectors, if we put them in the xy plane just for simplicity for now, if this is one vector and this here is another, what the cross product is doing is making another vector orthogonal to these two. So if this is in the xy plane, we'll have another vector in the z plane, or along the z axis specifically, and the length of that vector is going to be determined by the parallelogram created by these two vectors. So if we continue these two vectors to make a parallelogram, something like this, it's not the best drawing, but this area of the parallelogram created by these two vectors is going to be the size of the curl, the size of the vector perpendicular to this plane that these two vectors span. So this guy here is going to be a new vector, which is this guy. Okay. The next part I think worth talking about is Newton's second law. From any sort of introductory physics course, we should know Newton's second law as F equal to ma. We are going to be writing A slightly differently. This is going to be introducing some new notation, and this is going to be writing A in terms of the second derivative of position. All right, so we have A, which is equal to the first time derivative of velocity, and that is going to be denoted as v dot. This dot above it represents the time derivative. And the second derivative of position, these are both vectors. The second time derivative of position is going to be acceleration, and that's going to be noted by two dots. I guess these are both vectors here. R vector double dot. And so write it down here, F equals ma is going to become F equals m r double dot. And interestingly, where here r is just some position vector, but if we take the equation x double dot of t, so this is the acceleration equal to F naught over m. All right, this is just rewriting Newton's second law in the form we have here, but specifically in the x direction. If we integrate this once, integrate both sides, x double dot of t, and we're going to do it with respect to time, integral of F naught over m dt. What we are going to get is, from integration rules, one of these derivatives goes away, so we have x dot of t equal to F naught over m of t plus some constant, and this constant is going to be the initial velocity. And now if we take the integral again of both sides with respect to time, a little crunched, the integral of velocity is going to give us position, so x of t, and this is going to be equal to integral of f naught over m times t is going to be 1/2 f naught over m t squared plus v naught of t plus some constant, which is going to be the position in this case, initial position x naught. And then this can be simplified a little bit more. If we write this term f naught over m as the acceleration plus v naught of t plus x naught, what we have here is one of the more recognizable kinematic equations from any sort of introductory physics course, which is really cool. All right, we have a differential equation. You integrate it twice to solve for position, and we get a kinematic equation, which I know has tormented me for quite some time. I think the next and final thing worth going over is polar coordinates. So to start off, here we go. Polar coordinates. coordinates. These are going to be, I'll show you the conversion between the two here. X is going to be r cosine of the angle phi. Y is going to be r sine of phi. And this is interchangeable. I'll show you what r and phi are going to be. R is going to be square root of x squared plus y squared. And phi is going to be arctangent of y over x. All right, and then I think finding where we found Newton's second law, or I gave you Newton's second law in Cartesian, finding it in polar coordinates is probably worth it. It's good practice. So this would be the force is going to be the force in the r direction plus the force, I'll write this in the r hat direction plus the force in the phi hat direction. All right, and if you have not seen before these hats, this would be the r direction, or no, sorry, this x, y, we'd have a vector here, which is going to have a length of r and an angle, which will always be from the x-axis, starting at the x-axis, going to the vector. It's going to have an angle phi, and then the r hat direction is the direction it points, and the phi hat direction is perpendicular to the r hat direction. Doesn't exactly look perpendicular, but we'll say these are 90. Cool. So now we should be finding where before we were finding r double dot as the acceleration, we should be doing the same here. We have r, which is going to be equal, vector r is r in the r hat direction. And so the derivative of this, r vector dot, is going to be, we're going to have r time derivative times r hat plus r times the time derivative of r hat. Now this is going to be not just, I'll denote it as that for now, but the way we actually find that, we can denote r simply as r dot, but r hat dot is going to actually have a different value, and that can be found from a picture like so. If we do this, so if this is r1, r2, this is going to be the change in phi. I guess this would be, the change in phi. And then this here is the change in r. Oops. And so for very small changes in r, it's essentially going to be the change in phi. So what we have then is r vector dot is going to be equal to r time derivative of r hat, plus r multiplied by phi dot in the phi hat direction, right? Because the change in r is essentially going to be the change in phi in the phi hat direction, right? This is perpendicular to the r hat direction. And then taking the derivative of this again is going to get us the acceleration for Newton's second law. So r vector double dot now. Now this guy, r dot, just goes to r double dot. Oops. We just found what r hat was. That is going to go to plus r phi dot phi hat. And now we're going to take the derivative of this, derivative of this side. And that is going to time derivative of r is going to give us r dot. So we'll have r dot phi hat. And then time derivative with respect to the phi dot is going to give us r phi double dot phi hat. And then derivative of phi hat can be seen in another picture. If we do make this the origin, here's one, I'll make this a little bit. Here's this vector. Do this. Then here is the change in phi hat. Now this one may not be obvious. I guess this one's the change in phi. But this is going to be in the r hat direction. And I think probably a better way to show these is to actually show that it comes from, we can get it from these guys up here, the x and y. Yeah, I'll probably do that. The pictures are nice. They might be a little complicated to understand compared to algebraically what's going on. Okay, now where should I do this? I'll do this here. R hat is going to be denoted by x hat cosine of phi plus y hat sine of phi. And phi hat is going to be negative x hat sine phi plus y hat cosine phi. Looking at these, break it up into its components. Hopefully you can see where these sines and cosines are coming from. And doing the derivatives of these guys, right? Derivative, we'll do dr hat dt. You pull out the phis, phi dot, right? Derivative of stuff on the outside times the derivative of this stuff on the inside. All right, and then cosine goes to negative sine, still in the x hat direction because the x hat and y hat in this case are constants. And then sine goes to cosine, still with the y hat. And then these guys here just come from phi hat. So this becomes phi dot phi hat, which we found before, plugged into here. Now, same process for phi hat. So d phi hat dt is going to give derivative of stuff on the inside. All right, we're going to pull that out because they both share it. And then negative sine goes to negative cosine, still with the x-axis constant. sine goes to negative, cosine goes to negative sine, so minus y hat sine phi. And this guy is negative r hat. So phi, oh, I put a vector on this guy. This would be r hat dot. Phi hat dot is going to be negative, and then the stuff on the outside times r hat. Cool. So now finding our vector double dot with everything we know now. We have derivative of this guy goes to r double dot r hat. Oops, let's write that better. Plus now the derivative of this guy, r dot. Oops. And then derivative of r hat we found was phi dot phi hat. And then we have plus derivative of this guy, r dot phi hat, plus, and now derivative of this guy, r phi double dot phi hat. And now plus derivative of the phi hat. This gives r phi dot times phi dot in the r hat direction. Okay, this simplifies combining the r hats and factoring some stuff out. We have r double dot, oops, let's make this look better, r double dot minus r phi dot squared, this is in the r hat direction, plus r phi double dot plus, and then we have 2 r dot phi dot in the phi hat direction. All right, now this is now what we will use to plug into Newton's second law, F equals ma. Right, so F equals ma, but using our double dot, it's going to be it's going to be all this stuff plugged in. We can make this look nicer. What if I do? I'm going to do this guy. Well, maybe we will duplicate this, move it down here. But we can split this guy up. If we do F in the R direction, it should be M times R double dot minus r phi dot squared. F in the phi direction is going to be equal to r phi double dot plus 2 r dot phi dot. Well, I don't need the phi hat direction. Cool. This pretty much wraps up all the important stuff that I wanted to talk about. In the next couple of videos, hopefully I will be talking about some of the going over some examples and some problems that I think are some useful practice for what we went over today.